Hello, my name is Rachithan Chancharon, a lecturer in the Department of Mechanical Engineering at Chulalongkorn University. Today, I'll be explaining how microcontrollers and microcomputers can interface with external devices. This includes sending control signals to operate external components and receiving data from sensors for further processing. The Raspberry Pi is a great example of a modern microcomputer that offers flexible and powerful options for connecting to external devices. In this session, I'll provide an overview of the key methods used with the Raspberry Pi to control hardware and gather input from external sources. A microcomputer is of limited value if it cannot interact with external devices. To be truly useful, it must be able to send commands to external components and receive input from them. When developing systems with a microcontroller or microcomputer, it's essential to understand how to interface with external hardware. In this example, we use a Raspberry Pi, which provides a set of GPIO ports, short for General Purpose Input/Output. These ports allow the Raspberry Pi to communicate directly with sensors, buttons, LEDs, and other devices. The Raspberry Pi offers two main types of connections: a 40-pin GPIO header for general purpose I/O communication ports, such as USB and Ethernet. For more complex data transfer today, we'll focus on the GPI header. In the demonstration, GPIO pin 4 is connected with a blue wire to a push button, allowing the Raspberry Pi to receive input. Meanwhile, GPIO pin 12 is connected with a yellow wire to an LED, allowing the Pi to control output by switching the light on and off. To use the Raspberry Pi effectively with external devices, it's important to understand the correct methods for wiring and programming these interfaces. In this lesson, we'll explore the key techniques for working with GPIO to ensure reliable and efficient operation. Let's begin by understanding how a microcomputer connects to external devices using what is known as an input/output port, or GPIO, General Purpose Input/Output. In the digital domain, the microcomputer processes signals in the form of digital states, typically high or low, represented as binary 1 or 0. Physically, these states correspond to voltage levels. High usually means 3.3 volts, and low means 0 volts. However, in real-world applications, we must consider that digital signals can occasionally fall into a third state, undefined or not clear, especially if the wiring is incorrect or left floating. This undefined state can lead to unreliable performance. That's why proper electrical connections are crucial in microcontroller systems. The GPIO pins are designed primarily for transmitting and receiving signals, not power. Since these signals carry only a small amount of current, they cannot directly drive high-power devices such as motors or lights. Instead, we use interface circuits to safely link GPIOs with external loads. These circuits help convert voltage levels and isolate sensitive pins from potential damage. There are two common logic voltage systems used in electronics: TTL, transistor-transistor logic, which operates at 5 volts CMOS, complementary metal oxide semiconductor, which often operates at 3.3 volts. The Raspberry Pi follows CMOS logic and operates at 3.3 volts. Importantly, its GPIO pins are not 5-volt tolerant. Applying 5 volts to them can permanently damage the board. Some microcontrollers are labeled 5V tolerant, meaning they can safely receive 5V signals despite operating at 3.3V. The Raspberry Pi, however, is not one of them. Another important consideration is sequential processing. Microcomputers like the Raspberry Pi process one instruction at a time, in order. This means they can only handle one operation per cycle, which must be kept in mind when designing time-sensitive or parallel systems. To address the limitations of GPIO output current and signal reliability, developers often create interface circuits. These may involve transistors, logic-level shifters, or driver ICs to ensure that signals are safely and effectively transferred to and from external components. While GPIO is fundamentally digital, it's also possible to work with analog values using external modules, such as analog-to-digital converters, ADCs. This allows the system to interpret signal levels that represent varying physical quantities, such as temperature or light intensity. Each GPIO pin is programmable, meaning we can configure it in software as either an input pin to read data from sensors or an output pin to send control signals to actuators. Modern GPI interfaces also offer additional features such as internal pull-up or pull-down resistors, edge detection, and signal debouncing. In summary, GPIO provides a flexible and essential interface for connecting a microcomputer, like the Raspberry Pi, to the external world. But it must be used correctly and carefully, with attention to voltage levels, signal clarity, and power limitations. In Raspberry Pi, the input-output ports are referred to as GPIO, which stands for General Purpose Input-Output. In modern microcontrollers and microcomputers, these GPIO ports are programmable, meaning each pin can be configured as either an input or an output based on the application. Input pin. When configured as an input, the pin is used to receive data or signals from external components, such as sensors or switches. Output pin. When configured as an output, the pin sends signals to external devices like LEDs, motors, or relays. This flexibility makes GPI ports a powerful feature in modern development platforms. GPIO hardware. Features on Raspberry Pi. Modern GPIO pins come with built-in features that simplify system design. Programmable pull-up and pull-down resistors. Each GPIO pin can be internally configured to use a pull-up or pull-down resistor, which helps define the default logic level of the pin when no external signal is connected. This reduces the need for additional interface circuitry. Schmitt-trigger circuitry. The GPIO pins on Raspberry Pi also include Schmitt-trigger inputs to help filter out signal noise and debounce input, making them more reliable for reading button presses or other noisy signals. Operating voltage. Raspberry Pi GPIO pins operate at 3.3 volts logic levels. This means they are not 5V tolerant. Applying a 5-volt signal directly to a 3.3-volt pin can damage the Raspberry Pi. Therefore, any external device operating at 5 volts, 12 volts, or 24 volts must be interfaced properly using level shifters or interface circuits. Current limitations. Each GPIO pin can typically source or sync between 2 to 16 milliamps. This is sufficient for small loads like LEDs, but not for driving larger components directly. For higher power devices, external transistors or relays must be used. GPIO as input. Polling versus interrupt. When configuring a GPIO as an input, there are two main ways to read its state. Polling. This method repeatedly checks the state of the pin in a loop. It's simple to implement but inefficient in many applications, especially when multiple inputs need to be monitored. Interrupts with edge detection. Instead of constantly checking, the Raspberry Pi can monitor for a state change, called an edge, rising edge, low to high transition, falling edge, high to low transition. When an edge is detected, the system can immediately respond by triggering a function. This is more efficient and responsive. Raspberry Pi supports a feature called threaded callback, where each interrupt handler runs on a separate thread. This allows parallel execution of code in response to GPIO events without blocking the main program. GPIO as output, set, toggle, blink. When configured as output, the GPIO pin can set high, on, output 3.3 volts, set low, off, output 0 volts. You can control these states directly or use helper methods such as toggle. Automatically flip the pin state. If it's currently high, it becomes low. If low, it becomes high. Blink. Repeatedly turn the pin on and off based on a time interval. For example, you can set an LED to blink every 1 second. These functions are available through libraries like gpiozero, which simplify GPI management. The default blink interval is typically 1 second, but it can be customized programmatically. Summary GPIO equals programmable input-output ports. Each pin can be set as input or output Raspberry Pi. GPIO includes programmable pull-up, pull-down resistors, Schmitt-trigger noise filtering, 3.3V logic level, not 5V tolerant, max output current, approximately 2 to 16 milliamps. Input can be handled via polling, less efficient. Interrupts with edge detection, more efficient. Output control can include set, toggle, or blink. Use libraries like gpiozero to simplify programming and control. Let's continue. Here's a brief summary. The input-output ports on a Raspberry Pi are called GPIO, which stands for General Purpose Input-Output. These GPIO pins come with useful built-in features, including programmable pull-up and pull-down resistors, Schmitt-trigger circuits for noise filtering, the ability to act as interrupt sources, output current capabilities in the range of 2 to 16 milliamps. Specific calculations are beyond the scope of this clip. One important safety note: Raspberry Pi GPIO pins are not 5V tolerant. This means you must not apply a 5-volt signal directly to a GPIO pin, as doing so can damage the Raspberry Pi. Controlling GPIO with Python. In this course, we will use the Python programming language to control the GPIO pins. Python makes it easy to access and control the full functionality of the Raspberry Pi. To begin using GPIO in Python, we first import the RPi.GPIO package. Import RPi.GPIO as GPIO. It's important to understand that Python cannot access GPIO hardware directly. Instead, it communicates through a package like RPi.GPIO, which runs on top of the operating system, usually Raspberry Pi OS. Setting up GPIO. The first step after importing the package is to configure the GPIO numbering mode. The Raspberry Pi supports two types of pin numbering. Board uses the physical pin numbers on the header, 1 to 40. BCM uses the Broadcom chip's GPIO numbering, preferred in most cases. For example, to use BCM numbering, we write gpio.setMode, gpio.bcm. We can then configure GPIO pin 4 as an input with an internal pull-up resistor, gpio.setup4, gpio.in, pull-up down, gpio, tempud up. This command sets pin 4 as an input and enables the internal pull-up resistor. This eliminates the need for an external pull-up in many cases, simplifying circuit design. Reading input, polling. To read the status of an input pin, we can use a polling loop. For example, while true if GPIO.input4 equals GPIO.high, print open parenthesis. Input was high, close parenthesis, else. Print open parenthesis, input was low, close parenthesis. This continuously checks the status of pin 4 and prints the result. However, polling is not very efficient. The processor remains busy checking the pin in a constant loop. To reduce CPU usage, we can add a small delay. Import time while true if GPIO input 4 dominant. GPIO high, print input was high. Time sleep 0.01 delay for 10 milliseconds. This method still uses polling but consumes less processing power. Detecting input changes. Edge detection. A better alternative to polling is edge detection. Instead of checking the pin state continuously, the program waits for the pin to change from low to high or vice versa, called an edge. Here's how we do it. GPIO, wait for, sure edge 4, GPIO, rising, timeout, chuck 5000. Print, input was high. This waits for a rising edge, low to high, on pin 4. If no change occurs within 5 seconds, the function times out. This is still considered a form of polling, but it's more efficient since it doesn't require continuous looping. Event detection with callback. For even better performance, we can use interrupts with callback functions. Raspberry Pi allows GPIO to trigger a custom function when a pin changes state. Def handle, Shonker's input, cha-cha channel. Print, input was high. GPIO.add, event detect 4, GPIO.rising, callback equals handle input. This method is more efficient and allows other parts of the program to continue running without being blocked by GPI monitoring. Python can handle multiple threads, so the interrupt, callback, can run in the background while the main program continues. Summary of input techniques. There are 3 primary techniques for reading GPIO input. Polling, simple but CPU-intensive edge detection, wait for edge. Waits for state change with timeout callback with interrupts, event-driven and efficient. All these methods are supported by the RPi.GPIO library, and for more advanced use, there is an updated package called gpiozero that simplifies many of these tasks further. The GPIO0 library introduces a more advanced and user-friendly approach to GPIO programming compared to RPi.GPIO. It raises the abstraction level, making the code more readable and intuitive, especially for beginners. Instead of manually configuring GPIO pins as input or output, GPIO0 allows us to work with high-level abstractions like button, LED, or sensor, which simplifies development significantly. For example, if we want to use a push button connected to GPIO pin 4, we don't need to manually configure it as input or handle pull-up resistors ourselves. Here's how it works. From GPIO0, import button, wrench and button 4. That's it. By declaring the button this way, GPIO0 automatically sets pin 4 as an input and enables the internal pull-up resistor by default. This is important because physical push buttons, when released, typically leave the pin in a floating state. Pull-up resistors prevent this by ensuring the pin reads a default high value when not pressed. Polling with GPIO0. Just like in RPi.GPIO, we can implement polling with GPIO0. The structure is similar but more concise and readable. While true, if button is pressed, print input was high, else print input was low. This code checks the button state continuously in a loop. If the button is pressed, logic low becomes true due to the pull-up. It prints input was high. Otherwise, it prints input was low. Compared to RPi.GPIO, this version uses fewer lines and uses more human-friendly language. Instead of checking voltage levels, high or low, we simply ask if button dot is pressed. Edge detection with wait for press. To detect a state change, also known as an edge, we can use the wait for press method, button.wait for press. Print input was high. This waits until the button is pressed and then proceeds to the next line. Internally, it's still polling, but it simplifies the logic and eliminates the need to write a continuous while loop. You can also provide optional parameters to customize the wait behavior, such as timeouts, although the default settings typically suffice for simple applications. Callback and interrupt handling. Now let's explore callbacks, one of the most powerful features of GPIO0. A callback allows a function to be executed automatically in response to a GPIO event without needing a loop or manual check. Here's an example. From GPIO0 import button, def say hello, print hello, button 4, button, when I pressed, should run say hello. In this code, we define a function say hello that simply prints hello. We assign this function to button dot when pressed. Now, whenever the button is pressed, the Raspberry Pi interrupts the main program and calls the say hello function. This is an event-driven approach. It runs on a background thread, allowing the rest of the program to continue without delay. It's much more efficient than polling and is ideal for applications where timely response is needed. In traditional microcontroller programming, setting up interrupts can be complex. However, GPIO0 makes it simple by handling the interrupt mechanism behind the scenes. What about earlier versions of the Raspberry Pi? Let's return to the diagram and take a closer look. The Raspberry Pi is equipped with powerful and versatile hardware, especially when it comes to external connectivity. It supports two main types of ports for external communication. Communication ports such as USB, WIFI, and ETH/ERNET allow connection to peripherals and network devices. These are typical interfaces for microcomputers. GPIO ports, general purpose input/output, which are more flexible and allow direct electrical connection to sensors, actuators, buttons, LEDs, and other hardware components. In today's session, our focus is on the GPI ports, as they enable direct interfacing with external components at a low level. Python and GPIO control. When writing programs to control hardware on the Raspberry Pi, Python doesn't interact with the hardware directly. Instead, Python communicates with GPIO through dedicated libraries such as RPi.GPIO or GPIO0, which run on top of the Raspberry Pi's operating system. This indirect method of communication has both advantages and disadvantages. Disadvantage. There's an extra layer of abstraction, which can make control logic slightly more complex than bare metal programming. Advantage: it makes development more accessible and allows us to use a high-level language like Python to write clear, concise, and powerful control programs. GPIO capabilities. The GPIO hardware on the Raspberry Pi is quite sophisticated. Each pin can be configured as either input or output, programmed with internal pull-up or pull-down resistors, used with built-in Schmitt-trigger circuits for signal noise filtering, assigned as an interrupt pin to detect signal changes, edge detection. These features give the GPIO great flexibility and power. However, with increased capability comes increased complexity, especially when trying to manage all of this directly through low-level code. Simplifying GPIO with libraries. To make hardware programming easier, Raspberry Pi provides Python libraries such as RPi.GPIO, gives low-level control with more manual setup, gpiozero, a high-level abstraction that simplifies configuration and usage. These libraries manage the underlying complexity for developers. For example, instead of writing several lines to configure a pin as an input, enable a pull-up resistor, and set up an interrupt, gpiozero allows you to simply declare from gpiozero import button server button 4. Behind the scenes, gpiozero configures the pin as an input, enables the internal pull-up resistor, sets up interrupt detection for state changes from pin to button. This abstraction is powerful. Rather than thinking of pin 4 as a generic input, gpiozero lets us think of it as a button. This shift in terminology not only makes the code more intuitive, but also reflects real-world usage. For instance, push buttons are typically monitored not just for their high or low state, but for changes in state when a button is pressed or released. These transitions are known as edge events, e.g., rising or falling edge. Handling such transitions manually, especially when dealing with interrupts, can be difficult for new developers. With gpiozero, much of this is handled internally. Example: simplifying interrupts. Traditionally, to process button presses via interrupts, you'd need to configure the pin as an input, enable a pull-up resistor, write a function to be called when the button is pressed, register that function as a callback on an interrupt event. With gpiozero, all of this is reduced to button.when pressed equals my function. This single line tells gpiozero, monitor the button on the specified pin, automatically call my function whenever the button is pressed. This greatly simplifies development and allows you to focus on what your program should do, not how it connects to hardware internally. In summary, the Raspberry Pi supports both high-level communication ports, like USB and Wi-Fi, and low-level GPIO ports for direct device control. Python controls GPIO through libraries, RPi.GPIO or gpiozero, rather than directly. gpiozero simplifies GPIO usage by abstracting hardware details, providing intuitive object-oriented interfaces, like button, LED, automatically handling internal circuits like pull-up resistors, supporting interrupts and callbacks with simple syntax. This approach allows developers to focus more on functionality and logic and less on low-level hardware setup. By leveraging gpiozero, GPIO pins on the Raspberry Pi become much easier to use, even for beginners, while still allowing access to powerful hardware features. Let's explore further. What is an interrupt? An interrupt is a signal that temporarily halts the current execution of a program, allowing the system to respond to a specific event. Interrupts can be triggered by hardware or software, but in this discussion, we are focusing on hardware-level interrupts. A hardware interrupt is a signal generated by an external or internal hardware event, such as a button press, that forces the microcontroller to pause its current task and execute a separate piece of code, called an interrupt service routine, ISR, or interrupt handler. How interrupts work. Here's how the process generally works. The microcontroller is performing its normal tasks. An interrupt signal is triggered, e.g., a push button is pressed. The system immediately pauses its current operation. It jumps to the ISR and executes that function. Once the ISR is completed, the program returns to where it left off and resumes normal execution. This mechanism allows the microcontroller to respond instantly to important events without constantly checking or polling the status of those inputs. Example: keypad interrupt. In our example, we use a button press as the trigger for the interrupt. If the button is not pressed, no interrupt occurs, and the microcontroller continues with its usual tasks. As soon as the button is pressed, the system detects the signal change and executes the assigned ISR. In our case, the ISR simply prints "hello." Once this task is completed, the microcontroller resumes its previous task exactly where it left off. This setup is much more efficient than polling, which would require the system to constantly monitor the button's status. Efficiency in GPIO management. Using interrupts helps make GPIO management significantly more efficient. Instead of wasting resources constantly checking pin status, the system can focus on its primary tasks and only respond when necessary. This model is especially powerful on platforms like the Raspberry Pi, where applications don't interact directly with hardware. Instead, they communicate through Python packages like RPi.GPIO or gpiozero that run on the operating system. These packages manage the hardware layer and abstract the complexity of handling low-level hardware interrupts. This allows developers to use simple, high-level code while still leveraging advanced features like ISR and event-driven control. Summary: an interrupt allows a program to pause its current task and respond to an event. The event triggers a function called the interrupt service routine, ISR. Once the ISR is complete, the program returns to its original task. This approach is far more efficient than polling, especially for real-time event detection like button presses. On Raspberry Pi, users can implement interrupts easily using Python libraries without needing to manage hardware directly. This abstraction enables developers to write cleaner, more efficient code while fully utilizing the hardware's capabilities. Here we have a simple but powerful example, using a button to control an LED through the Raspberry Pi. On the hardware side, this looks straightforward: a button, an LED, a couple of resistors, and 2 GPIO pins. But in reality, the execution is quite complex. When we press the button, the circuit must handle voltage changes, ensure the signal doesn't float when idle, and limit the current through the LED. Normally, these details require careful management of electronics and low-level programming. Fortunately, Python and the gpiozero library take care of the heavy lifting for us. Instead of dealing with raw registers or hardware drivers, we can simply declare LED equals LED open parenthesis, 12 close parenthesis button equals button open parenthesis, 4 close parenthesis. With just these lines, the library automatically configures the pins, manages pull-down resistors, and even handles button bouncing. The most elegant part is the event-driven programming. By writing button when pressed equals LED, on button when released equals LED. Off, we connect the button's events directly to the LED's behavior. That means when the button is pressed, the LED lights up, and when it's released, it turns off. No complex loops or constant polling required. So while the electronics and low-level control are actually complicated, Python allows us to express the functionality in just a few clean lines. This is the real advantage of combining hardware with high-level programming. We can focus on what the system does, rather than worrying about how every tiny detail works behind the scenes. When working with GPIO on the Raspberry Pi, there are 2 common approaches to detecting input changes: polling and interrupts. Both methods can be used to achieve the same outcome, responding to an event such as a button press, but they operate very differently in terms of how they use system resources and how quickly they respond. In the polling method, as shown in the first example, the program continuously checks the state of the button inside an infinite loop. If the button is pressed, the LED is turned on. If it is released, the LED is turned off. A short delay, sleep 1, is added to reduce the load on the CPU, but the loop is still running all the time, even when nothing changes. This makes polling simple to understand and implement, but it is inefficient. The CPU remains busy checking the button repeatedly, and the reaction speed is limited by the loop delay, meaning the system may not respond instantly. The interrupt method, as shown in the second example, works in a completely different way. Instead of continuously checking the button, the program sets up event handlers that tell the Raspberry Pi to automatically run a specific function when the button is pressed or released. For instance, button dot when pressed equals LED dot on turns the LED on the moment the button is pressed, and button dot when released equals LED off turns it off the moment the button is released. With interrupts, the CPU is free to perform other tasks or remain idle until an event actually occurs. This makes interrupts much more efficient as they eliminate unnecessary looping, and they provide a faster response because the event is handled immediately. In summary, polling is straightforward and useful for small or simple projects where timing is not critical, but it wastes CPU resources and may respond more slowly. Interrupts, on the other hand, are ideal for real-time applications or situations where power efficiency and quick reaction are important. By allowing the hardware to wake up the program only when needed, interrupts offer cleaner code, lower CPU usage, and near-instant responsiveness. In GPIO0, both dot value and dot source can be used to connect one device to another, but they work in different ways and are suited to different programming styles. The first method uses the dot value property, as shown in the value example. Here, the program runs in a continuous loop, repeatedly setting the LED's value equal to the button's value. This approach is straightforward and easy to understand. When the button is pressed, its value changes, and the LED updates accordingly. However, because it relies on a while-true loop with a short delay, sleep 0.01, it behaves like polling, constantly checking the state and updating the LED, even if nothing changes. This means the CPU is being used continuously, which can be inefficient, especially in larger projects or when multiple inputs are being monitored. The second method uses the dot source property, as in the source example. By setting LED source equals button, you directly link the LED state to the button state. Once this link is established, the LED automatically updates whenever the button changes, without the need for a manual loop. The pause function simply keeps the program running while the gpiozero framework handles the updates in the background. This is more efficient than the dot value loop because it removes the constant polling and delegates the work to the library's event-driven system. It also produces cleaner, shorter, and more readable code. When we compare the two techniques, the dot value method is better suited for simple experiments, debugging, or when you need to perform additional logic on each loop iteration. It gives you explicit control over when and how updates occur, but at the cost of efficiency. On the other hand, source is the more elegant and efficient choice for directly linking devices without extra processing. It's ideal for projects where the output should always mirror the input without additional computation. However, source can be less flexible if you need to insert custom logic between the input and output states, since it creates a direct binding between devices. In summary, value offers simplicity and control, but uses more CPU due to continuous looping, while dot source is more efficient and concise, but less suited for cases requiring intermediate logic. The choice depends on whether your priority is explicit control or streamlined, event-driven linking. In GPIO0, a composite command is a high-level instruction that performs multiple low-level hardware actions in a single step. This means that instead of manually controlling each GPIO pin individually, you can issue a single command, such as motor.forward, and the library will handle all the necessary pin signals behind the scenes. This greatly simplifies motor control programming and improves code readability, especially for beginners or when creating quick prototypes. In the provided example, the motor object is initialized with two GPIO pins, pin 17 and pin 18, which are connected to the control inputs of a motor driver module, such as an L293D, L298N, or another H-bridge circuit. The motor itself is wired to the driver's output terminals, and the driver receives its own power supply, typically 5 volts or 12 volts, depending on the motor's requirements. The Raspberry Pi's GPIO pins only send low-current logic signals to the driver. They do not supply motor power directly. This separation ensures that the Pi is protected from the high current demands of the motor while still retaining full control over its operation. When motor.forward is executed, GPIO0 automatically sets one control pin high and the other low, which signals the motor driver to supply current in the correct direction, causing the motor to spin forward. Without composite commands, you would have to manually set each GPIO pin's state in the correct sequence, increasing the complexity of the code and the risk of mistakes. With composite commands, this process is abstracted, making the code cleaner and less error-prone. This approach offers several advantages. It is intuitive, reduces the number of code lines, and allows the developer to focus on the logic of the project rather than the intricacies of hardware control. However, the abstraction may be limiting in highly customized or unconventional motor control setups where direct pin manipulation is required. For most standard applications, though, composite commands strike an excellent balance between simplicity and functionality, making them a practical choice for controlling motors in Raspberry Pi projects. When working with a Raspberry Pi, simple input and output devices allow the system to interact with the physical world, enabling it to sense events and control external components. The GPIO pins act as the interface for these devices, and by using Python with the gpiozero library, we can manage them in a simple and intuitive way. GPIO0 provides high-level classes for each type of device, which means we don't need to manually configure pins or write complex low-level code. Most of the setup happens automatically in the background. Digital inputs are devices that send an on or off signal to the Raspberry Pi. An SPDT, single-pole double throw, switch, for example, has 3 terminals and can connect the common terminal to one of 2 outputs, producing either a high 1 or low 0 signal. In Python, we can use the digital input device or button class from GPIO0 to detect the switch's position. A push button works in a similar way, but only makes contact when pressed, making it useful for momentary actions. With GPIO0's button class, checking whether the button is pressed is as straightforward as reading its press property. Digital outputs allow the Raspberry Pi to control devices that respond to on-off signals. A basic example is an LED, which can be switched on or off by sending a high or low signal from a GPIO pin. In GPIO0, the LED class provides simple methods such as dot on and dot off to control it. This makes tasks like blinking an LED or indicating system status extremely easy to implement. For analog inputs, the Raspberry Pi needs some assistance because its GPIO pins cannot directly measure variable voltages. Devices such as potentiometers output a continuous range of voltages depending on their position, so we use an analog-to-digital converter, ADC, such as the MCP 3008 chip, to read them. With GPIO0's MCP 3008 class, we can read a potentiometer's position as a value between 0.0 and 1.0, allowing us to use it for adjustable controls like volume, brightness, or speed. Analog output on the Raspberry Pi is achieved through pulse width modulation, PWM, which rapidly switches a signal on and off to simulate varying voltage levels. This is particularly useful for controlling devices like dimmable LEDs or motors. With gpiozero's PWM LED class, for example, we can adjust an LED's brightness by setting its dot value property anywhere between 0.0 off and 1.0 fully on, allowing for smooth fading effects. Overall, GPIO0 and Python make it easy to interface with simple I/O devices by abstracting away the technical details and providing device-specific classes. This not only speeds up development, but also makes the code easier to read, maintain, and expand. Whether we are reading switches and buttons, controlling LEDs, measuring a potentiometer, or dimming lights with PWM, GPIO0 turns complex hardware interactions into clear, concise Python commands. When interfacing a push button and an LED with the Raspberry Pi, it is important to follow both proper wiring practices and correct software configuration to ensure safe and reliable operation. In this example, the push button is connected to GPIO4 using a blue wire, while the LED is connected to GPIO12 using a yellow wire. GPIO4 serves as the input pin for detecting button presses, and GPIO12 serves as the output pin for controlling the LED. Because GPIO12 supports hardware PWM, We can use it not only to switch the LED on and off, but also to control its brightness smoothly. For the push-button connection, one terminal of the button is wired directly to GPIO 4, and the other terminal is connected to one of the Raspberry Pi's ground GND pins. In software, we will enable the internal pull-up resistor on GPIO 4 so that the pin reads a high signal when the button is not pressed and a low signal when it is pressed. This method avoids floating inputs and eliminates the need for an external resistor in basic projects. For the LED connection, the anode, positive leg, is wired to GPIO 12 through a current-limiting resistor, typically between 220 ohms and 330 ohms, to protect both the LED and the Raspberry Pi's GPIO pin from excessive current. The cathode, negative leg, is connected to a ground pin. The resistor ensures the LED operates within safe electrical limits while maintaining adequate brightness. By using a PWM LED object in Python's gpiozero library, GPIO 12 can provide pulse width modulation, which allows for fine-grained control over LED brightness instead of a simple on-off state. In software, we can declare the button and LED devices with button equals button open parenthesis, 4 close parenthesis, and LED equals PWM LED open parenthesis, 12 close parenthesis. When the button is pressed, we can set LED value equals 1.0 for full brightness, or choose any value between 0.0 and 1.0 for dimming. PWM LED also provides built-in methods such as LED.pulse to create smooth fading effects without complex timing code. This combination of proper wiring in the gpiozero library's high-level abstractions allows for intuitive, readable code that makes hardware interaction more accessible while still leveraging the Raspberry Pi's advanced capabilities. When interfacing electronic components and sensors with a microcontroller or microcomputer, such as the Raspberry Pi, it is crucial to understand the SVG concept: signal, voltage, power, and ground. This principle is the foundation of nearly all electronic wiring schemes. In any connection, the power V line provides the necessary voltage to operate the device, the ground G line completes the electrical circuit, and the signal S line transmits data or control information between the device and the microcontroller. Correctly identifying and wiring these three connections ensures both functional operation and device safety. In practice, these connections are often organized into a bus interface where multiple devices share common power and ground lines while each has its own signal line, or, in some bus protocols, shares a signal line with specific addressing. For example, I2C and SPI are common digital bus standards that follow the SVG principle. In analog connections, the signal line carries a continuous voltage that represents a range of values, e.g., from 0 volts to 3.3 volts on a Raspberry Pi. Whereas in digital connections, the signal line alternates between discrete high and low voltage levels to represent binary data. Analog signals are more susceptible to noise, but can represent fine variations, while digital signals offer robustness and easier error detection. Because wiring directly to the Raspberry Pi's GPIO pins can quickly become complex, especially when using multiple sensors, it is highly recommended to use a Raspberry Pi HAT, hardware attached on top, designed for structured SVG wiring. Many HATs offer labeled connectors for signal, voltage, and ground, reducing wiring mistakes and ensuring secure connections. This is particularly beneficial when working with multiple sensors or actuators that have SVG interfaces, such as ultrasonic distance sensors, infrared proximity sensors, temperature and humidity modules, and analog to digital converter boards. These HATs often integrate protective circuitry, signal conditioning, and sometimes level shifting to match voltage requirements, further improving reliability. By combining an understanding of the SVG concept with bus communication protocols and organized wiring through a Raspberry Pi HAT, developers can create cleaner, safer, and more scalable hardware setups. This approach is especially valuable in educational and prototyping environments, where quick reconfiguration and clear wiring are essential. When comparing Arduino's C++ style programming with Python's gpiozero library, the difference in coding style, abstraction and ease of implementation becomes very clear. In the first example of controlling an LED's on and off state, the Arduino approach requires setting up the pin mode in the setup function, then explicitly turning the pin high or low inside the loop function with delays in between. This structure is rigid and verbose, but gives full control over the hardware at a low level. In contrast, gpiozero in Python abstracts away much of the pin configuration, allowing a single object, LED12, to encapsulate all LED control methods. This makes the code more concise, readable, and faster to write, especially for beginners or rapid prototyping. The gpiozero library also provides intuitive built-in methods such as on, off, toggle, and blink. These methods eliminate the need to manually write repetitive loops for LED blinking or toggling. For example, a simple LED.blink command replaces several lines of Arduino code that manually switch states and delay between them. Furthermore, in Python, these operations are non-blocking if desired, allowing the program to handle other tasks concurrently without complex timing logic. Using Python and gpiozero for LED control can be as simple as a loop that calls LED.on and LED.off with sleep intervals, but the real power comes from event-driven programming. By binding an LED to a button press, we can eliminate constant polling loops. In the example where a button on GPIO 4 is connected to an LED on GPIO 12, we assign LED.on to button when pressed and LED.off to button when released. This event binding means the LED responds instantly to button presses without consuming CPU cycles in a busy loop, something that requires more complex interrupt handling in Arduino code. Overall, Arduino offers a more traditional, hardware-focused programming experience with granular control, which is ideal for resource-limited microcontrollers. However, gpiozero in Python emphasizes simplicity, abstraction, and rapid development. For projects involving Raspberry Pi, especially where multitasking, quick prototyping, or integration with higher-level libraries is needed, gpiozero provides a far more streamlined approach. This shift from manual pin control to object-oriented device handling makes hardware interaction both accessible and efficient. This slide expands our gpiozero control capabilities by introducing two more advanced use cases: PWM-LED for variable brightness control, and multi-LED control objects like RGB LED, LED board, LED bar graph, and traffic lights. The PWM-LED class enables fine-grained control over LED brightness by setting a duty cycle between 0, fully off, and 1, fully on. This allows not only simple on-off control, but also dimming, smooth pulsing, blinking, and toggling effects. For example, by setting LED value equals 0.5, the LED operates at half brightness, while commands like pulse create a continuous fade-in and fade-out effect. This approach is ideal for status indicators or aesthetic lighting where variable intensity is needed. In addition to single LEDs, gpiozero supports controlling multiple LEDs as a single object. The LED board class, for instance, allows you to define multiple pins for multiple LEDs and then control all of them in one line of code. By assigning a tuple to LED's value, each LED can be switched on or off simultaneously according to the corresponding tuple element. This approach scales well for multi-light arrangements, such as RGB LEDs for color mixing, LED bar graphs for level indicators, or traffic lights for simulation projects. In summary, gpiozero's PWM-LED and multi-LED control classes extend LED control far beyond basic blinking. PWM-LED introduces smooth and adjustable lighting effects, while objects like LED board make managing multiple LEDs efficient and organized, reducing repetitive code and enabling more complex, visually appealing hardware projects. Similarly, another commonly used device is the buzzer. When we want to generate a sound or a beep using the buzzer's speaker, gpiozero provides a convenient way to control it through a dedicated object called buzzer. With this object, we can easily issue commands such as buzzer.on to activate the buzzer.off, to stop the sound buzzer.toggle, to switch the state between on and off. The buzzer object makes it simple to manage sound output with just a few lines of code. Beyond buzzers, GPIO also supports objects for controlling various actuators, including DC motors, servo motors, other types of motor drivers. This is all made possible through a concept known as a composite signal, where multiple GPIO pins are grouped and defined as a single device object. Once the object is defined, you can control the device as a whole, making the programming process much easier and more intuitive. This image provides another example, this time demonstrating how to control a motor using gpiozero. In the sample code, we rotate the motor forward, stop, rotate it in reverse, stop again, and repeat. This is done easily using composite commands in Python. To control the motor, we connect two GPIO pins, in A and in B, to a motor driver, which in turn drives the motor. In this example, in A is connected to GPIO pin 4 and in B to GPIO pin 14. We then import the motor class from the gpiozero library and define the motor as follows. From gpiozero import, motor, motor, forward 4, backward 14. Now controlling the motor is simple. You can use motor.forward, motor.backward. This allows you to rotate the motor forward or backward with just a single line of code. In contrast, if we were programming a microcontroller directly, achieving the same result would require multiple lines of code, careful timing control, and possibly handling conflicts between overlapping commands. But with GPIozero, the package handles all of that complexity for us. You can simply command the motor to rotate forward for 5 seconds, then backward for 5 seconds using code like this. Motor dot, forward dot, sleep open parenthesis, 5 close parenthesis, motor dot, backward parentheses, sleep open parenthesis, 5 close parenthesis. With just a few lines of code, the motor responds as expected, smoothly and efficiently. GPIozero defines a variety of objects to represent different hardware components. In this diagram, you can see a tree structure that categorizes these objects into groups. This object-oriented approach to programming with Python makes the code more structured and modular. However, it also means the concepts can be slightly more complex to understand at first. That said, once you start building real projects, this structure becomes extremely useful. It allows for clearer, more scalable code and simplifies the process of managing multiple devices through the GPIO. Using GPIO can be made much easier with the right tools. In many of the examples shown in this clip, I use an add-on board called the Leaf HAT, which was developed by Thai engineers. This HAT simplifies hardware connections by organizing the GPI pins into a structured bus system. For example, GPIO pins 24, 25, 26, and 27 are arranged in a groove that follows the SVG bus standard, allowing external devices to be connected with just a single 3-wire cable for power and signal. The Leaf hat includes several built-in components such as a push button connected to pin 13, a joystick, an RGB LED module using the WS2812B, which is controlled via a pulse-based protocol serial communication pins for RX/TX. One of the main benefits of using a hat like this is that it organizes and aligns the pins properly, making wiring easier, safer, and more reliable. Today, I've tried to share a few ideas that can help simplify hardware development and GPIO management using this approach. When developing hardware connections through GPIO using Python packages, we've introduced several important concepts. However, for a deeper understanding, you should refer to the resources linked in this slide. These include documentation on the Raspberry Pi GPIO system, the RPi.GPIO package, the gpiozero package. You may also want to explore Arduino references for comparison, especially if you're coming from a microcontroller background. Today we focused on 2 major GPIO libraries for Raspberry Pi, RPi.GPIO and gpiozero. As we've seen, each package offers different levels of abstraction. RPi.GPIO gives more direct, low-level control. gpiozero simplifies development with high-level, object-oriented interfaces. As the Raspberry Pi ecosystem continues to evolve, we can expect new packages to emerge that make hardware programming even easier and more efficient. This is a key advantage of using a microcontroller platform like Raspberry Pi with the Python programming language, especially under a full operating system. It allows developers to manage hardware through software packages, abstracting the complexity and allowing more focus on functionality. By leveraging these packages, we can unlock the full potential of the Raspberry Pi in a more accessible and powerful way. Thank you for watching. See you again in the next video.